In chemistry, a nonmetal is a chemical element that mostly lacks metallic attributes. Physically, nonmetals tend to be highly volatile, have low elasticity, and are good insulators of heat and electricity. Chemically, they tend to have high ionization energy and electronegativity values, and gain or share electrons when they react with other elements or compounds. 17 elements are generally classified as nonmetals, most are gases, one is a liquid, and a few are solids. Moving rightward across the standard form of the periodic table, nonmetals adopt structures that have progressively fewer nearest neighbors. Polyatomic nonmetals have structures with either 3 nearest neighbors, as is the case with carbon, or 2 nearest neighbors in the case of sulfur. Diatomic nonmetals, such as hydrogen, have 1 nearest neighbor, and the monatomic noble gases, such as helium, have none. This gradual fall in the number of nearest neighbors is associated with a reduction in metallic character and an increase in non-metallic character. The distinction between the 3 categories of nonmetals, in terms of receding metallicity, is not absolute. Boundary overlaps occur as outlying elements in each category show less distinct, hybrid-like or atypical properties. Although 5 times more elements are metals than nonmetals, 2 of the nonmetals, hydrogen and helium, make up over 99% of the observable universe, and 1, oxygen, makes up close to half of the Earth's crust, oceans and atmosphere. Living organisms are also composed almost entirely of nonmetals, and nonmetals form many more compounds than metals. Definition and properties. The marvelous variety and infinite subtlety of the non-metallic elements, their compounds, structures and reactions, is not sufficiently acknowledged in the current teaching of chemistry. J. Zuckerman and F. C. Nashod in Studle's Chemistry of the Non-Metals. There is no rigorous definition of a non-metal. They show more variability in the properties than do metals. The following are some of the chief characteristics of nonmetals. Physically, they largely exist as monatomic gases, with a few having more substantial diatomic or polyatomic forms, unlike metals, which are nearly all solid and close-packed. If solid, they generally have a submetallic or dull appearance and are brittle, as opposed to metals, which are lustrous, ductile or malleable. They usually have lower densities than metals, are poor conductors of heat and electricity when compared to metals, and have significantly lower melting points and boiling points than those of metals. Chemically, the nonmetals have relatively high ionization energy and high electronegativity. They usually exist as anions or oxyanions in aqueous solution, generally form ionic or interstitial compounds when mixed with metals. Unlike metals, which form alloys, and have acidic oxides, whereas the common oxides of the metals are basic, applicable elements. The elements generally classified as nonmetals include 1 element in group 1, 1 in group 14, 2 in group 15, 3 in group 16, most of group 17, and all of group 18. The distinction between nonmetals and metals is by no means clear. The result is that a few borderline elements lacking a preponderance of either nonmetallic or metallic properties are classified as metalloids, and some elements classified as nonmetals are instead sometimes classified as metalloids, or vice versa. For example, selenium, a nonmetal, is sometimes classified instead as a metalloid, particularly in environmental chemistry, and astatine, which is a metalloid and a halogen, is sometimes classified instead as a nonmetal. Categories. Nonmetals have structures in which each atom usually forms bonds with nearest neighbors, where n is the number of valence electrons. Each atom is thereby able to complete its valence shell and attain a stable noble gas configuration. Exceptions to the rule occur with hydrogen, carbon, nitrogen and oxygen. Atoms of the latter 3 elements are sufficiently small such that they are able to form alternative bonding structures, with fewer nearest neighbors. Thus, carbon is able to form its layered graphite structure, and nitrogen and oxygen are able to form diatomic molecules having triple and double bonds, respectively. The larger size of the remaining non-noble nonmetals weakens their capacity to form multiple bonds, and they instead form two or more single bonds to two or more different atoms. Sulfur, for example, forms an 8-membered molecule in which the atoms are arranged in a ring, with each atom forming two single bonds to different atoms. From left to right across the standard form of periodic table, as metallic character decreases, nonmetals therefore adopt structures that show a gradual reduction in the numbers of nearest neighbors, 3 or 2 for the polyatomic nonmetals, through 1 for the diatomic nonmetals, to 0 for the monatomic noble gases. A similar pattern occurs more generally, at the level of the entire periodic table, in comparing metals and nonmetals. There is a transition from metallic bonding among the metals on the left of the table through to covalent or van der Waals bonding among the nonmetals on the right of the table. Metallic bonding tends to involve close-packed centrosymmetric structures with a high number of nearest neighbors. Post-transition metals and metalloids, sandwiched between the true metals and the nonmetals, tend to have more complex structures with an intermediate number of nearest neighbors. Non-metallic bonding, towards the right of the table, features open-packed directional structures with fewer or zero nearest neighbors. As noted, this steady reduction in the number of nearest neighbors, as metallic character decreases and non-metallic character increases, is mirrored among the nonmetals, the structures of which gradually change from polyatomic, to diatomic, to monatomic. As is the case with the major categories of metals, metalloids and nonmetals, there is some variation and overlapping of properties within and across each category of nonmetal. Among the polyatomic nonmetals, carbon, phosphorus and selenium, which border the metalloids, begin to show some metallic character. Sulfur is the least metallic of the polyatomic nonmetals, but even here shows some discernible metal-like character. Of the diatomic nonmetals, iodine is the most metallic. Its number of nearest neighbors is sometimes described as 1 plus 2, hence it is almost a polyatomic nonmetal. Within the iodine molecule, significant electronic interactions occur with the two next nearest neighbors of each atom, and these interactions give rise, in bulk iodine, to a shiny appearance and semiconducting properties. Of the monatomic nonmetals, radon is the most metallic and begins to show some cationic behavior, which is unusual for a nonmetal. Carbon, phosphorus, sulfur, and selenium, consistent with their higher coordination numbers. The polyatomic nonmetals show more metallic character than the neighboring diatomic nonmetals. They are all solid, mostly semi-lustrous semiconductors with electronegativity values that are intermediate to moderately high. Sulfur is the least metallic of the polyatomic nonmetals given its dull appearance, brittle comportment, and low conductivity, attributes common to all sulfur allotropes. It nevertheless shows some metallic character, either intrinsically or in its compounds with other nonmetals. Examples include the malleability of plastic sulfur and the lustrous bronze appearance and metallic conductivity of polysulfur nitride. The polyatomic nonmetals are distinguished from the diatomic nonmetals by virtue of having higher coordination numbers, higher melting points, and higher boiling points, and having wider liquid ranges and lower room temperature volatility. More generally, they show a marked tendency to exist in allotropic forms, and a stronger inclination to catenate, and have a weaker ability to form hydrogen bonds. The ability of carbon to catenate, in particular, is fundamental to the field of organic chemistry and life on Earth. All of the polyatomic nonmetals are solids, and all are known in either malleable, pliable or ductile forms. Most also have lower ionization energies and electronegativities than those of the diatomic nonmetals. Diatomic nonmetals. 7 nonmetals exist as diatomic molecules in their standard states: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They are generally highly insulating, highly electronegative, non-reflective gases, noting that bromine, a liquid, and iodine, a solid, are both volatile at room temperature. Exceptions to this generalized description occur at the boundaries of the category. Hydrogen has a comparatively low electronegativity due to its unique atomic structure. Iodine, in crystalline form, is semi-lustrous, and a semiconductor in the direction of its layers, both of these attributes being consistent with incipient metallic character. The diatomic nonmetals are distinguished from the polyatomic nonmetals by virtue of having lower coordination numbers, lower melting points, and lower boiling points, and having narrower liquid ranges and greater room temperature volatility. More generally, they show less inclination to exist in allotropic forms, and to catenate, and have a stronger ability to form hydrogen bonds. Most are also gases, and have higher ionization energies and higher electronegativities than those of the polyatomic nonmetals. Noble gases. 6 nonmetals occur naturally as monatomic noble gases: helium, neon, argon, krypton, xenon, and the radioactive radon. They comprise a group of chemical elements with very similar properties. In their standard states they are all colorless, odorless, non-flammable gases with characteristically very low chemical reactivity. With their closed valence shells, the noble gases have the highest first ionization potentials in each of their periods, and feeble interatomic forces of attraction, with the latter property resulting in very low melting and boiling points. That is why they are all gases under standard conditions, even those with atomic masses larger than many normally solid elements. The status of the period 7 congener of the noble gases, element 118, is not known. It may or may not be a noble gas. It was originally predicted to be a noble gas but may instead be a fairly reactive solid with an anomalously low first ionization potential, due to relativistic effects. On the other hand, if relativistic effects peak in period 7 at element 112, copernicium, element 118 may turn out to be a noble gas after all, albeit more reactive than either xenon or radon. Elemental gases: hydrogen, nitrogen, oxygen, fluorine, chlorine, plus the noble gases are collectively referred to as the elemental gases. These elements are gaseous at standard temperature and pressure. They are also distinguished by having the lowest densities, lowest melting and boiling points, strongest insulating properties, and highest electronegativity and ionization energy values in the periodic table. It is not known if any synthetic elements with atomic number above 99 are gases. If it transpires that copernicium and flerovium are gaseous metals at or near room temperature, as some calculations have suggested, the category of elemental gases may need to be subdivided into metallic and non-metallic gases, organogens, CHONPS, and biogens: carbon, hydrogen, oxygen, nitrogen, phosphorus and sulfur are sometimes referred to or categorized as organogens. CHONPS elements or biogens. Collectively, these 6 nonmetals are required for all life on Earth. They are further distinguished, in comparison to the halogens and noble gases, by their general capacity to form allotropes, high atomization energies, intermediate electron affinities, reactivity combined with low toxicity, ability to form alloys with metals, and the weak or neutral, acid-base character of their group hydrides. Other nonmetals: selenium, and possibly boron, silicon, arsenic and tellurium, plus the organogen elements are sometimes categorized together as other nonmetals. The first 5 of these differ from the organogens. Comparison of properties. Physical properties are listed in loose order of ease of determination. Chemical properties run from general to specific, and then to descriptive. Allotropes. Many nonmetals have less stable allotropes, with either non-metallic or metallic properties. Graphite, the standard state of carbon, has a lustrous appearance and is a fairly good electrical conductor. The diamond allotrope of carbon is clearly non-metallic, however, being translucent and having a relatively poor electrical conductivity. Carbon is also known in several other allotropic forms, including semiconducting Buckminster fullerene. Nitrogen can form gaseous tetranitrogen, an unstable polyatomic molecule with a lifetime of about 1 microsecond. Oxygen is a diatomic molecule in its standard state. It also exists as ozone, an unstable polyatomic nonmetallic allotrope with a half-life of around half an hour. Phosphorus, uniquely, exists in several allotropic forms that are more stable than that of its standard state as white phosphorus. The red and black allotropes are probably the best known. Both are semiconductors. Black phosphorus, in addition, has a lustrous appearance. Phosphorus is also known as diphosphorus, an unstable diatomic allotrope. Sulfur has more allotropes than any other element. All of these, except plastic sulfur, have non-metallic properties. Selenium has several non-metallic allotropes, all of which are much less electrically conducting than its standard state of gray, metallic, selenium. Iodine is also known in a semiconducting amorphous form. Under sufficiently high pressures, just over half of the nonmetals, starting with phosphorus at 1.7 gigapascals, have been observed to form metallic allotropes. Abundance and extraction. Hydrogen and helium are estimated to make up approximately 99% of all ordinary matter in the universe. Less than 5% of the universe is believed to be made of ordinary matter, represented by stars, planets and living beings. The balance is made of dark energy and dark matter, both of which are poorly understood at present. Hydrogen, carbon, nitrogen, and oxygen constitute the great bulk of the Earth's atmosphere, oceans, crust, and biosphere. The remaining non-metals have abundances of 0.5% or less. In comparison, 35% of the crust is made up of the metals sodium, magnesium, aluminium, potassium and iron, together with a metalloid, silicon. All other metals and metalloids have abundances within the crust, oceans or biosphere of 0.2% or less. Nonmetals, in their elemental forms, are extracted from brine, Cl, Bri, liquid air, No, Ni, Rkix, minerals, CFPi, natural gas, He, and from ores, as processing byproducts, She, and Rn. Applications in common. For prevalent and specialty applications of individual nonmetals, see the main article for each element. Nonmetals do not have any universal or near-universal applications. This is not the case with metals, most of which have structural uses, nor the metalloids, the typical uses of which extend to oxide glasses, alloying components, and semiconductors. Shared applications of different subsets of the nonmetals instead encompass their presence in, or specific uses in the fields of cryogenics and refrigerants. He, No, F and Ni, fertilizers. Ps, Cl and She, household accoutrements. He, No, F, Ni, Ps, Cl, R, She, Br, Ki, Xe and Rn, industrial acids. F, Ps and Cl, inert air replacements. Ni, S, R, Kr and Xc, lasers and lighting. He, No, F, Ni, S, R, Kr and Xc, and medicine and pharmaceuticals. He, O, F, Cl, Br, Xe and Rn. The number of compounds formed by nonmetals is vast. The first 9 places in a top 20 table of elements most frequently encountered in 8,427,300 compounds, as listed in the Chemical Abstracts Service Register for July 1987, were occupied by nonmetals. Hydrogen, carbon, oxygen and nitrogen were found in the majority of compounds. The highest rated metal, with an occurrence frequency of 2.3%, was iron, in 11th place.